Time is 2:30, so let's get started here. So project number 1 is due now, and I think all of you have turned it in. If for some reason I'm incorrect, please come talk to me after class if you didn't turn it in. We will start talking about project number 2 today, and that will be due February 19th. Ideally, it would be nice if I would have it due before the test, and I could give it back to you then before you take the test, so you get some feedback that way. But I think it's just sometimes hard to always do that. So I thought the best course of action would be just to make it due after the tests. But I do highly recommend that you at least look at every problem on the project before the test, because there will be likely to be some similar problems. Let's briefly talk about the tests. We will have a full review for the tests on Thursday, February 12th. But I just want to remind you that this is going to be somewhat of a computer-based test. So you will need to use the computers that are at your desk to solve particular problems. You will be given a paper copy of the exam, and that's where you need to write all of your answers on. So to some respect, the computer is like an is like how you would use, let's say, a calculator on maybe some other classes' tests. With the test, there will be a formula sheet that I will make available to you on my website. It's going to be basically just about the same as what you see currently for the test number 1 formula sheet that was given, I guess, in 2014. Also, you will have access to all my R programs, because I don't want you to have to memorize R code, but you definitely need to be comfortable with writing R code in a test situation, because obviously you have a limited amount of time. Also, you should be comfortable with my programs that are available on the web. You should know, if I ask you to find, as we will talk about here today, a confidence interval for an odds ratio using a logistic regression model, that should take you just a few seconds to find that corresponding code in my placekick.r program, if you need to look at my previous code. Now, with every answer that you give on the test, you're going to need to show your work. Just like you would do in any other kind of math or statistics exam, you need to show your work. So if you just simply wrote down the number 2 for an answer for a particular problem, it was the odds ratio, I would not give you full credit. I want you to show your work. So for example, that could mean actually giving the equation for the odds ratio, so I have a little bit of idea of how you actually obtain the number 2. Or it could also mean instead you could write R code on the exam. Now, writing R code is not a requirement for the exam, but if you want to include it, you can, as a way to show your work. Now, if you remember from, I think it was the first day of class, I first mentioned this. Test number 1 from 2014 is available on my website. It's on the Graded Materials webpage. What I recommend that you do is, before maybe even our next class, take it as a practice in a test situation where you have an hour and 15 minutes to complete the exam. That way you'll have maybe an idea of before you start really studying heavily for an exam, you'll have an idea of what areas you need to work on, and if you can complete it in an hour and 15 minutes. Now, the material for that for my 2014 exam, the material that was covered was all of Chapter 1, like we did, and it goes up to page 251 in my notes, my current set of notes. So basically, it's everything before section 2.2.4. Now, for our tests, I anticipate that I will also include section 2.2.4, just because of where we are in the semester when the test is given. Once I write the test, I'll know more about it. I haven't written the test yet. I've just barely started it, and hopefully, I hope by the next class I will have written the test. Okay, so that's all of the announcements that I have. Are there any questions?
Are our programs going to be given as they are on your website right now?
Yes.
With comments as well?
Yes.
Okay.
Yeah. So if you had me for a class before, it's the same format. Other questions? Okay. We left off in the notes talking about hypothesis testing. on page 230. So we talked about a wall test for a parameter beta sub r. In particular, our hypotheses are HO. We are picking one beta from our model, and just to be general, we're calling it the rth beta. Is that equal to 0 or not? Because if it is equal to 0, that suggests that the x has really no relationship with the probability of success. And so we looked at a wall test to do this, and we have discussed problems that occur with wall-based inferences. And so generally speaking, a better approach, unless you have a very large sample size, is the likelihood ratio test. We've talked about likelihood ratio tests before, so some of this will be reviewed. It just would be a little bit different in the context of now we are using a logistic regression model. So again, our likelihood ratio test statistic is this thing that we call lambda. And lambda is a ratio of two different likelihood functions. One that's maximized under the constraint that HO is true, which for us basically will be the logistic regression model without x sub r in it, because beta sub r is equal to 0. So what you would do then is get your beta hats for this null hypothesis model, get your corresponding pi hats for that model, plug it into the likelihood function that we've seen in the past for the pi's. Then on the denominator is the maximum possible value of the likelihood function under HO or HA. Now, this will end up being basically the model that includes all your explanatory variables, so including the x sub r. And the reason being is because the more explanatory variables you add to the model, typically the better the fit will be the model. I shouldn't say typically, the better the fit the model will occur. Now, if you've had a class like Stat 870, you know that you've already have known that in terms of a normal linear regression model. If you remember that coefficient of determination, r squared, you can keep on adding terms to your model, and r squared keeps on going up, 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 no matter what. Well, similarly here, the maximum possible value of the likelihood function under HO or HA is the HA model that has the additional explanatory variable. Okay, so let's say then for notational purposes that when we look at the HO model, notice you don't see the rth explanatory variable in there. Let's say that the corresponding maximum likelihood estimates are beta hat, and then we have a superscript 0 there to indicate it's under HO. So that's how all my beta hats are denoted. My corresponding pi hat will be denoted in the same way. Then for the HA model, which does include that rth explanatory variable, we have the same thing, but now we're going to use a superscript A to denote these are the estimates under the HA model. Then our negative 2 log lambda, remember we take that little transformational lambda so we can use a chi-square distribution with it. Negative 2 log lambda looks like this, where this beta hat, and that is actually a bolded beta hat with a superscript 0, indicates that's a vector of all my beta hats together. Just a simple notational way to combine everything. And my beta hat with an A, and that is a bold beta there, again means the same thing, but now for the beta hats from our alternative hypothesis model. So what that looks like then, if I do some simple algebra using properties of logarithms, I can break this fraction up into two different components here. So we can say maybe that's step 2. This is step 1. And then let's actually put in what the likelihood function is. But we substitute now the estimated parameters for the actual true parameters. So here is my maximum possible value of the likelihood function under the HL model, maximum possible value under the HA model. Or I've distributed in that minus sign. So you can look back in your notes previously when we've looked at the likelihood function, log likelihood function before. And notice we have some terms that have things in common. So notice how I have a y there, I have a y there, so we can combine those terms. Also, we'll be very colorful today. I have a 1 minus y here, I have a 1 minus y here, and so I combine the terms there. And so you can see then basically what this likelihood ratio test is doing is comparing two estimates of the pi's. Basically it's going to give us a numerical measure to determine, well, which one's better? The ones under HO or the ones under HA? We can compare then negative 2 log lambda to then the chi-square 1 distribution. And again, well, let me ask you this. What happens to lambda as evidence it grows against the null hypothesis? What's going to happen to lambda? It's going to get closer to 0 or closer to 1? It's going to get closer to 0, lambda is. Because the HO model is not as good. That maximum possible value of that likelihood function under HO is going to be maybe a lot lower than the one under the HA model. And so then if lambda gets lower, what happens to negative log lambda? It gets higher. Okay, so what we're doing is we're looking again for large values of negative 2 log lambda, and that's what the chi-square distribution with 1 degree of freedom helps us do. Get the 1 minus alpha quantile from it to make that judgment. So when should you reject? Well, when negative 2 log lambda is greater than the 1 minus alpha quantile from a chi-square 1. So how do we calculate the p-value? Can someone give me an expression for the p-value? So p in p-value stands for
The
probability. Thank you. So probability of what?
probability of obtaining the test statistic, given that the null is true.
Test statistic greater than.
Okay, I need one more thing here.
Q.
Excuse me?
Q.
Q? What do you mean by Q? Well, I guess I put a Q there.
It's height.
Excuse me?
Height.
What's a hat?
It's I think it's by height. I think. Oh,
That's good.
yes. Good.
I don't care what letter you use. You know, I often use A because it's the first letter of the alphabet. If A is a random variable with a chi-square 1, we're looking at what's the probability it's greater than the observed value that we get from negative 2 log lambda. That's our p-value.
Why did you use? You used Q previously. Why did you? Was that just a random letter you chose?
I used Q previously.
Yeah, when we
I g-
did
I-
lambda, when we talked about likelihood ratio test previously.
I guess I don't remember using Q. Maybe I'm wrong. I thought I used A. It doesn't matter what letter.
Okay.
Okay. Now you can generalize this to a case where maybe you're testing more than one beta at the same time, and you want to test, you know, maybe beta 1, beta 2, beta 3. Are they equal to 0 or not? With all the other maybe remaining explanatory variables in your model. Let's say we have a lowercase q to represent the number of betas that we're testing equal to 0. In that case, you do exactly the same thing as what we've done here, essentially, except for now you use a chi-square sub q distribution. So let's take a look at an example of how we can do this with the place-kicking data. Let me just make sure. Yep. Okay. Let's see here. So we have the change variable and the distance variable in our model. And what I would like to do is some hypothesis tests. In particular, I want to test, is beta 1 equals 0? I'm going to do it with a walled and a likelihood ratio test. Also, I'm going to separately test, is beta 2 equal to 0? With a walled and likelihood ratio test. So we've looked at this kind of a model before. If you remember, just as review, we use the GLM function to estimate these models. And in the formula argument, that's where we tell R what our model is. So my response, what we often call Y, is what's called good in the data set. And then I put my explanatory variables on the right-hand side of the tilde. And so my x1, let's say, would be change. My x2 would be distance. I say family equal binomial, link equal logit to specify logistic regression. And I specify my data as in place kick. when I summarize then the results that I get from the GLM function, this is what I have. So here's beta hat 0, here's beta hat 1, and here's beta hat 2. Now we've kind of looked at this kind of output before, and I try to appeal to some intuitiveness based upon maybe what you've seen in the past in other courses. This Z value that you see there, that is our Z sub 0 that we use for a wall test. And then the PR parentheses greater than the absolute value of Z in parentheses, that's our P value for a wall test. So what I've done is now summarize then the results that we see in that output. So for the change model, my null hypothesis says beta 1 is equal to 0. What does that mean in terms of my model? What's my model if I were to write it out? Beta 0 plus, how about we say beta 2 times distance? Okay. My alternative hypothesis model is, yep, the full model. And I'm going to run out of room. Sorry, this is not going to be pretty. That's why I like to type. I know it will be all pretty when we look at it. My handwriting's not the best. So, if we go back to the output again, for change, we can see that my test statistic is negative 2.31. Also, we can see that the p-value then is 0.0208. And it's a relatively small p-value, so we would reject. So what this is saying is that it's not really common to get a test statistic this large if beta 1 was equal to 0. So that tells you, hey, maybe something's going on wrong here. Maybe beta 1 does not equal 0. And that's why you say don't reject. Now, I have to admit, and this is what's discussed now below the table, is that it's probably better in this particular situation to say maybe there's marginal evidence. Because if I were to use alpha 0.05, obviously p-value is less than alpha, so you would reject. What happens if you say alpha 0.01, which is a common thing to do? Well, then you don't reject. So, should you base your conclusion, so strongly on alpha 0.05 or alpha 0.01 chosen? No. What's better to say is that, well, there is some evidence here. I would say more it's marginal evidence, but there is some evidence that change does have an effect on the probability of success. Now, on the other hand, let's take a look at distance. So I'm testing beta 2. Is that equal to 0 or not? In the output, the test statistic's negative 13. P-value in the output, just to make sure you're familiar with what this means. So you see less than 2e negative 16. Well, that's as far as, I guess you could say, as small as that my computer will go in terms of calculating p-values based upon the numerical precision that's available to it. So this represents 2 to the negative 16th power, which is obviously a number that's extremely small in terms of close to 0. So the p-value is actually something less than that. So that's why I wrote the p-value like that. I hope I said that right. 2 times 10 to the negative 16th power. So I would reject HL. Yes, there is strong evidence that distance has an effect on the probability of success. So that's a wall test. Now, without looking ahead of the notes, what do you think the likelihood ratio test is going to conclude? Do you think it will conclude something similar to what the wall test did? I'm getting some no's, maybe some yeses. The answer is yes. The reason being is because wall tests, essentially, and as does do likelihood ratio tests, get better as the sample size gets higher. In this case, I have a relatively large sample. I have 1,428 place kicks. So I would expect both the walled and likelihood ratio tests to perform almost equally well. And that means then that they'll perform very similarly. Now, if my sample size was maybe 30, let's say, I would not necessarily have that expectation. And if I had the choice between a walled test and a likelihood ratio test, I would pick the likelihood ratio test, no question. So even though we talk down about walled tests or walled confidence intervals, they can still be good, but you just often need a larger sample size in order for them to work out than maybe other statistical procedures. Okay, so how can we perform a likelihood ratio test in R? There are actually a number of different ways. And I'm going to go over a few different ways. The reason being is because some are easier than others. But unfortunately, these easier ways are not necessarily always available to us when we have more complicated model structures. So that's why it's good for you to, at this stage of the class, to make sure that you understand how to do a likelihood ratio test using these few different methods. Okay, so the easiest way is to use a function called ANOVA. Notice the capital letter there, that's important. I like to call this the capital ANOVA function. It is actually in the CAR package. CAR package is not in R by default. You will need to download it if you want to use it. And this is how it works. Relatively simple. So first of all, if you haven't done this already, say library CAR to indicate you want to use the CAR package after you have downloaded and installed the package. And then you just simply say ANOVA, and then for the mod argument, put in where you have saved the model information from GLM. And then you need to specify, well, what kind of test do I want? A likelihood ratio test. They just use LR for short. And this is what I get. This test here is testing exactly the same thing that we saw in the previous table. So for example, this p-value here for change says it's comparing the model that just has distance in it to the model that has distance and change in it. So exact same hypotheses. I want to emphasize that because we're going to look at something shortly that's not exact same hypothesis. And we can see here with this both p-values, they're very similar to what we had with the wall test. So same kind of conclusion. The second way then to do a likelihood ratio test is to use the ANOVA function. But notice there's a little a there. This is in the stats package. And the stats package is what automatically comes with R. It also contains a GLM function, in case I never said that before. And this is how you use ANOVA. Now the argument is object equal mod.fit2, where I've stored the results, and you say test equal chi-sq for essentially, we're using this chi-square approximation, so that's where the name comes from. And this is what we get. The main thing to focus on is these statistics here. These are -2 log lambda statistics. And perhaps I didn't point that out before. Sorry. That right there was -2 log lambda statistics. But you will notice that they are not exactly the same. Let me see if I can get this on one page. Oh, almost. There we go. Well. There we go. They're on the same page now. They're not exactly the same. The one for distance is. And this is doing the test that we want. Given that changes in the model, let's evaluate should distance, is there an effect that distance has on the probability of success? So in other words, it's testing beta 2 equals 0 versus beta 2 does not equal 0. The thing that's different then is this right here. Okay. That's because the little ANOVA function is not testing the hypotheses that we want. Instead, what it's testing is this. The null hypothesis model is you have no explanatory variables at all. The alternative hypothesis model, change and only changes is in it. Well, why? Well, the way that the little ANOVA function is set up is to construct a set of sequential hypotheses. If you remember the way that we specified our model, we had change first, distance second. And so what this does, it basically adds one variable at a time to the model and tests the corresponding sequential hypotheses. So if I had a third variable, then that distance then would be would assume change was in the model for both the null and alternative hypotheses, but it wouldn't have the third variable at all in the model for any of the hypotheses. So you have to be careful when you use the little ANOVA function, because actually, most likely, this is not the kind of hypotheses that you want to test. Yeah.
ANOVA function just test the sequential, yeah, but the others test the partial.
Given everything else is in the model,
Yeah,
let's test this one variable.
yeah, it's just a partial testing.
It's testing exactly what was in that table that I gave you earlier in the notes for that wall test. Okay, so in terms of the hypotheses will be equivalent to the way that I have presented the wall tests. Okay?
Suppose we have just one variable, let's say we just have to change, these two should be the same.
Yeah. Yep.
So this is a conditional test.
I wouldn't call it a conditional test just because of the terminology that statisticians use for what conditional tests mean. Rather, I would say we are conditioning on, let's say, all the other variables being in the model, and we're focusing on one. Sorry to be precise in that terminology, but a conditional test means something else for statisticians.
So do you recommend that we use the big ANOVA?
Use the big ANOVA when you want to do something like this. Now, next I'm going to show you one use of the little ANOVA function that can be very useful. But yeah, I would never use the little ANOVA function in this manner, but it's good for me to show you what happens because obviously their names are almost the same. Okay. Now, here's where the little ANOVA function can come in handy. And that is, you can use it in a slightly different manner. Suppose you actually estimate an HO model of interest. Let's say the model that just has distance in it without change. And, you know, when we want to test, actually go back up, sorry. There we go. So when we want to test, oh, let's get a good color. When I want to test this and focus on the model-based way of stating the hypotheses, what I've just done is now estimate. This has been one problem with tablet PCs. I've been using tablet PCs now since 2003. And it's been one problem, and that is whenever you write on a table in Word, often what can happen is your writing like moves after you get done writing. Anyway, I'll do it the old-fashioned way. I'll point. So focus on those models there. We have fit the alternative hypothesis model. That's what we started off with. That's what's in mod.fit2. And I am just fitting now the null hypothesis model at the bottom of page 35. Is that right? Yeah, bottom of page 35, top of page 36. Okay. So here's my null model if I want to change, if I want to test the change variable. And what you can do with the little ANOVA function is this. Put in your HO model first as the first argument. Put in your HA model second. Again, specify, basically you want a likelihood ratio test. And look what we get. right here under this column called deviance. I'll explain what deviance means shortly. We get the same test statistic that we had been getting previously with the capital ANOVA function. So you can get the right test. You just have to know how to use the ANOVA function the little ANOVA function properly. And this is something we're going to foreshadow some stuff later in the semester. There are going to be times where that big ANOVA function, we're not going to be able to use it because it hasn't been programmed for certain kinds of models. And so what we might have to do is always resort back to the little ANOVA function. And so that's why it's good to know now how you can use it. Okay. So here's a question. So notice I've been using the word ANOVA a lot, but we're not doing analysis of variance here. We're essentially comparing likelihood functions. Why do you think why do you think this function is called ANOVA? Actually, I wish it wouldn't be, but it is. Don't blame me. Well, what do you do in analysis of variance? So if you took like Stat 802, you're often testing terms of a model, right? Maybe even doing it in a sequential manner at times. Well, that's essentially what we're doing here, but now instead we're using likelihood ratio tests rather than sums of squares. In fact, if you were to take Stat 802, where it would be taught in R versus SAS, you would be using the ANOVA function to compare models, because it will do the test, the F-based tests based upon sums of squares. So anyway, that's where the origin of the name comes from. Now, you could also program in the likelihood ratio test yourself, the lambda statistic yourself, and do -2 log lambda yourself too. And I'm not going to talk about it here, but what I've done is given you some code that does it. And I recommend that you read it because it makes sure that you understand, more of this -2 log lambda. How is it actually calculated? And that's one of the nice little benefits of using a software package like R, is that you can actually program in these expressions, these equations that were given you. You can program in and you can duplicate essentially exactly what these nice functions give us automatically. So please take a look at that on your own. One interesting thing to point out, although it's not too useful, or it's not useful in too many situations, let's say you want to fit a model without any kind of explanatory variables at all. So in other words, you want to fit this particular model here. You can do that in R by specifying the number 1 after the tilde, rather than the names of any explanatory variables. Okay, so let's talk about this thing called deviance. The word deviance, you saw it in the output, even though I didn't really point it out in too many places. You also saw the word like maybe residual deviance, or you saw the word dev for deviance. What this basically refers to is that it's the amount a particular model deviates from another model using the -2 log lambda statistic. That's all. So it's how one model deviates from another as measured numerically using this -2 log lambda statistic. That's all. So you might want to put here basically equation 1 on page 231. Now there are two types of uses of deviance, the name deviance, that often occur. One particular thing is called the residual deviance. And basically all that means is this. You want to compare a model of interest, such as the model that has just distance in it, and you want to compare it to basically a model that's equivalent to, how should I put it, I want to be very careful with my terminology so I don't screw you up here. We're basically, how about I just say this? Say it this way. You want to compare a model of interest, let's say a model that has just distance in it, to another model that is essentially using the observed proportion of successes for every distance. So let's say, let's see now, let me go back here in my notes. So page 226, I'm going to do a split screen here. I'll go back to there. So on the bottom will be page 226. Remember when we found the observed proportion of successes at every distance? And I think in total there are probably about 40 unique distances. And so what the residual deviance does is that for one of its models, it essentially says, let's estimate pi simply the best that we could, and that is by using the observed proportion of successes. So if I have about 40 distances, that means I have a parameter that has 40 parameters. I have a model that has 40 parameters. Okay? Where if I use only distance itself to estimate the probability of success, how many parameters do I have? 2. The beta 0 and beta 1. So you can see what you're doing with the residual deviance. You're comparing a model that's not that complex, with just distance in it, to a model that's extremely complex, that has as many parameters that you could have possible. Since this is as many parameters as you could have possible, this kind of model is called a saturated model. So it's like, if you have maybe like a towel that is, been dipped into some water, and it's holding essentially as much water as it can. That's the towel is saturated. Well, a model is saturated by having as many parameters as possible. You can never have more parameters than the number of observations. So in this particular case, I have essentially, since I'm looking at the binomial form of the data, I have essentially 40 observations. Okay? So for example, I would estimate, let's say, pi hat here to be 0.67. I would estimate pi hat here to be 1. I would estimate pi hat here to be 0.9835.
So you have so each of the distances is a predictor?
Well, each of the observations is predicted by the proportion of successes. Where with the distance-only model, I'm just using, and it just so happens the way this is organized, I'm using the numerical value of distance to help me relate to relate it to the probability of success, and that's why I only have 2 parameters. I hear silence. I'm afraid that I did confuse you. Are there any questions? This is often, unfortunately, a kind of confusing topic. Let me try another way too, to explain it, because actually it's quite simple in the end. Excuse me. So let's say that we have a regular old linear regression model. Okay, just one variable. I estimate the model, and this is what I get for the estimated model. Okay. What's the residual?
Observed minus predicted.
Excuse me?
Observed minus predicted.
Observed minus predicted, yeah. So let's say y minus y hat, right? Okay. What this is basically doing is this. You have this very simple model here. You're using 2 parameters. And you are comparing the result that you would get from that simple model to what you could say is another model that simply says, okay, I'm going to just use the observed value instead. where I don't necessarily care about explanatory variables. Okay, that's a residual. Now notice the name here, residual deviance. How does one model deviate from another model? And we're essentially, instead of calculating y minus y hat, the way that we're actually calculating a residual, which it would be probably new to many of you, go back eventually. The way that we're calculating a residual is, let me do some erasing too. And we'll do it orange. This is how we're calculating a residual. I want to avoid that summation there. So the residual, and let me actually do this here too. So the residual for the ith observation is everything that's highlighted there, everything but the summation. It's just a different way to calculate a residual rather than y minus y hat. And so that's what the residual deviance is measuring. It's just comparing, again, the two models. One using essentially what was observed, in our case would be the proportion of successes, to what we're saying is a possible model for my data. The model that just has the distance of the place kick in there. Does that help? Would anybody like me to try another explanation? I'd be happy to.
So which
I do have one more.
which again is the saturated model?
The saturated model is the one that has as many parameters as you possibly could have. And that means the number of parameters equals the number of observations. When we have the binomial form of our data, the number of observations, it ends up being actually the number of unique combinations of the distances.
So
The number of rows of our data set.
So when you have the two models, one with only the intercept and one with the intercept and the
I don't have a model that has just only the intercept here. That was another discussion that we were having before, when I was trying to show you how you could calculate a likelihood ratio statistic. So remember, I said read this on your own. That's the only time that I mentioned. You could have a model that has only an intercept in it, and that's only shown for demonstration purposes of how to calculate negative 2 log lambda. Okay. Any questions? Because we will be using the residual deviance a lot, so it's important that if you do have questions, you need to raise them. Or you can always just postpone asking a question and save it for next time after you've let this sink in a little bit. Okay, so that's the residual deviance. Now there's also something then called the null deviance. And this is actually a place where the model that we were just talking about comes up. The null deviance is usually not very useful, but you see it in the output a lot, so that's why I want to bring it up. Excuse me. And all it does is compares the model that has no explanatory variables in it to the saturated model. So essentially what this is doing is giving a negative 2 log lambda statistic that's like testing overall or any of the or how should I say? Can I just deal with a model that has no explanatory variables in it? Maybe a model, maybe we don't need to get very complex here. It's like saying, well, distance doesn't really matter for a place kick. Let's do hypothesis tests to determine that. And so that's what the null deviance measures. And let's actually go back to some output that we've seen so we can see these terms pop up. So for example, here's residual deviance. Here's the word deviance as well. And if you'll notice, if I subtract these two numbers, I get that one. We'll talk about why that happens shortly. With each of these deviances, since it's a negative 2 log lambda statistic, it has a corresponding degrees of freedom. Those are the degrees of freedom there. Let's keep on going back here. So notice this is the, we don't want to do that little ANOVA output. There we go. There we go. So this is when we estimated the model has change in distance in it. Notice what's shown here: null deviance, residual deviance. So what this is testing right here is 770.5, negative 2 log lambda. That is testing the following. My null hypothesis model is beta 0 plus beta 1 times change plus beta 2 times distance. The alternative hypothesis model is what I abbreviate as SAT model, for saturated model. That's what that's testing. And what we could do, and we'll actually do this some in chapter 5, because at least right now I don't want to focus on this particular test. What we will do in chapter 5 is actually use this as a measure of goodness of fit. How well does my overall model fit the data? Because what you're doing, you're comparing a model of interest to basically a perfectly fitting model. And that's what you do in a goodness of fit situation.
What will the saturated model look like? But if you were to...
If I were to write it out in terms of parameters?
Yeah.
Yeah, that was my alternative way of presenting it. Sometimes it get kind of confusing. Essentially, it will look like this. I'm going to, instead of using betas, I'm going to use a gamma to help differentiate it. So let's say I have some parameters that are gammas. And this is what the model looks like. So for every observation in my data set, I have a separate gamma. So you can see I would have, 1,428 different 1,428 different gammas for this particular form of my Bernoulli form of my data. Does that help? I mean, you can even write it another way. If you don't like that, you can say gamma 1 times, I'm going to write an indicator function with a 1 in it, meaning that this indicator function means if it's the first observation, this I is a 1. If it's not for the first observation, it's a 0. So this would be another way that you could write it as well. And you can actually maybe see the different things there. I think, I could be wrong though, but I think in placekick.r there is actually an example where I do something like that. I fit a saturated model to the data. You take a look at it. If you can't find it, just do a simple example of your own. Maybe make up your own data set that has 5 observations in it, and simply set it up so that you have 5 different explanatory variables, so that you can get essentially what will be a perfect fit. If you have problems doing that, let me know, and I can show you how to do that. But I think in the placekick.r program, there is an example of that. Okay. Now these deviance statistics, what we are going to use them for in chapter 2 is as follows. Excuse me. The deviance statistics essentially can be calculated as an intermediate step to do a hypothesis test such as what we started off with at the beginning of class. So again, consider the situation, I shouldn't say again, but let's consider the situation such as this, where I have a null hypothesis model, I have an alternative hypothesis model. Notice the difference between the 2 different models. One has 1 variable, one has 3 variables. Make sure you add the little superscripts in your notes on page 239. I unfortunately left them off. then what the residual deviant, if I were to estimate this null hypothesis model, what the residual deviance in the output will give me is a negative 2 log lambda statistic for this hypothesis test, where I have one explanatory variable and I'm comparing it to a saturated. If I have Bernoulli, if I have Bernoulli responses, this is what my negative 2 log lambda looks like. So here would be essentially what we had seen before to be like the alternative hypothesis pi hat. If I'm working with binomial response data, there's my estimated pi hat for that particular model. Now the residual deviance for what's my alternative hypothesis model up, even farther up, the residual deviance would be testing this. If I were to use GLM and estimate this model. And so what ends up happening is that, if you notice how I have some equation numbers here. I have equation 2 for the residual deviance for the null hypothesis model. I have equation 3 for the residual deviance of the alternative hypothesis model. If I were to take equation 2 minus 3, I get equation 1 that's located on page 231. That was the very first equation that we saw for the likelihood ratio test. And so what this tells you is then that you have this another way to do the likelihood ratio test of interest. Estimate the null hypothesis model, get the residual deviance. Estimate the alternative hypothesis model, get the residual deviance, subtract the 2, and you get your negative 2 log lambda that's actually of interest to you. So for example, let's say again that I wanted to test these hypotheses. So in other words, I'm interested in change itself. And what I'm going to do, if you remember, mod.fit2 contains the results from that alternative hypothesis model. If I estimate now my null hypothesis model, put that in mod.fit.ho, what I can do is as follows. There is a component inside my mod.fits that's called deviance, and it gives me my negative 2 log lambda statistic for both models. Also, there's a component called df.residual, which gives me my corresponding degrees of freedom that's needed for those hypothesis tests. So what I can do is I can subtract, in both cases, and get my negative 2 log lambda statistic of interest. I can calculate my p-value, similar to what we've done in the chapter 1 notes when we did a likelihood ratio test. And here are the results. My negative 2 log lambda statistics is 5.2455, which is exactly what we've seen a few times before. And same p-value. Okay, so what I've done in this section is hopefully not confuse you. But what I've done is I've shown you a number of different ways to get this likelihood ratio test that we want. Especially for tests, but even so for projects, try to use the easiest method. If the easiest method is not going to work out for you, go to one of these more complicated methods. This last method that I just showed you, actually, when I was first teaching categorical class, that's what the only one that I would use. But I think I think it is helpful for students to know those easier methods. And so, especially on a test situation where you're pressed for time, take advantage of like the capital ANOVA function. Take advantage of even at times the little ANOVA function to do this because it will be quicker. Okay, so that takes us to page 242. Well, let's just pause there and take a look at project number 2. So if you have a copy of that, please take it out. Okay. So problem number 1 continues with this Olestra data that we had saw before, but now we're going to approach it from a logistic regression perspective. As I mentioned, I think it was last time that, if you have a 2x2 contingency table, you can actually reform your data into a data frame and actually approach it from a logistic regression point of view. And I think I mentioned that in the homework, there was an example with the polio data set that does that exactly. And essentially what you're doing is some of the stuff that's in the homework for the polio example, you're doing it here now for the Lestra or Lestra data. And so part A then asks, I want you to take that contingency table structure, so what I often will refer to as C.table, convert it to a data frame that you can use with the GLM function. Now in the homework, it's demonstrated for the polio example of how to do that. Also in my book, on the very bottom of page 133, it's shown for the bird data set, how to do that. So use that same type of coding, it's like about 3 or 4 lines of coding, and convert the data to this format here. Part B then says, well, what I want you to do is add a variable to the data set. And one way to do that is, suppose your data is in set 2, just say $, your new variable name, and notice how there's just 2 rows here, and I want to add a 0 and a 1. What that's going to do is give us a numerical way to denote our explanatory variable, which will be, what type of potato chip was eaten, the Lestra kind or the regular kind. So essentially, this is like the change variable in the place-kick data set. It's a binary variable, basically representing a categorical explanatory variable. Now, later in the chapter 2 notes, you will learn about how R can automatically do this conversion for you from let's say, a categorical variable that has just names to it to one that has numerical values so that you can actually estimate a model with it. R has ways to do that conversion for you. We'll learn about that later, but I thought it would be good for you now to do this simplified addition. Okay. Part C then says, well, estimate a logistic regression model using then the type of potato chip as the explanatory variable, and then, well, the binomial side effect response as your response. Part D involves the stuff that we're going to do next in the notes, where you're going to do some odds ratios. And what you're going to notice is that the odds ratios that you get from logistic regression will be the same as what you get from using a 2x2 contingency structure in section 1.2. Part E covers the stuff that we just did. Do a likelihood ratio test to determine, well, is the type of potato chip related to, well, the probability of having side effects. Part F is a problem dealing with section 2.2.4. And then part G, what should be a very simple problem. And that is, well, suppose the amount of potato chips that each individual consumed was available. I think we maybe even talked about that before, that, or maybe we didn't. You would think that the more that someone eats the potato chips, maybe the more susceptible that they might be to having these side effects. And in fact, I think that was one of the other hypotheses that the researchers had, is that the people who were eating like the WOW type of potato chips were eating more because they know, hey, it doesn't necessarily have as much fat in it, so I'm going to eat more than what I would normally. And so because of that, maybe that's what's causing these side effects. Okay? Well, how can we make that determination then, given this logistic regression setup? It should be a very simple problem of how to make that determination. Or what would you do? Okay, so that's problem number 1. problem number 2 is number 21 from the book. And let me get into Wendell's journal here. So what this involves is something called a lethal dose level, or LD for short. And this is of interest in situations where, let's say that you have a, I'll give you this example. Suppose that you have an apartment that's maybe 900 square feet, and you want to know, what level of a pesticide needs to be applied in that apartment to kill all scorpions in it. Okay, and you want it to be 90% effective. So in other words, you're looking for the lethal dosage level in order to kill 90% of all scorpions. That's a problem that's often of interest for people who are dealing with those kinds of problems. It was actually of interest to me when I first thought of this example when I was teaching Categorical a long time ago. A real quick story. So I started my career at Oklahoma State University in the Department of Statistics, and I was teaching Categorical down there. And in my apartment, my wife and I, we were having scorpion problems. Seriously. I mean, I never had lived in Oklahoma before, or even really farther south in Kansas before, and we were having scorpion problems. And one night, probably about 2, 3 a.m., I wake up to my wife screaming. It's because there's a scorpion in our bed. And so we quickly, get the sheets off the bed, and this little thing's moving around on the bed. Oh, by the way, in case I didn't mention, it was stinging her. That's why she was screaming. And so it's moving around. We're off the bed. It's like, well, we got to get rid of it. So what do? So I yank my alarm clock off my nightstand, and I start going down, trying to slam and kill that thing. And scorpions, if you've never experienced scorpions before, or haven't any experience with scorpions before, they have a way of being able to spread their body out kind of flat. And since it was on a bed, which is a soft surface, I really had to hit that thing many, many times. So anyway, so that got me thinking about lethal dose levels. And fortunately, our apartment complex did start spraying our apartment on a regular basis. What it actually took was I put the scorpion in a baggie, and I took it over to the apartment office, and the next morning saying, see, yes, we do have scorpion problems. Enough about that little story. So in this case, in these kinds of problems, it's what's called an inverse prediction problem, in case maybe you've heard of it in another setting, where now you know what pi is, but you want to find what x is. So if pi is 0.9, and let's say that this is your model, what you do is you put 0.9 in here and you solve for dose. And so what part A then of this problem number 21 asks you to do is come up with a general expression for dose. And all of this is just some simple algebra. Then part B asks, okay, I actually give you how to actually find a confidence interval for dose, since we know what pi is. Now we want to find a confidence interval for dose. How do you do that? And it's something that's very closely related to how the Wilson interval was derived. So I want you to give me some justification. I actually give you the expression itself in the book. I want you to give me some justification for the expression itself and how the interval is found. So that's 21. 22 continues talking about lethal doses, but now in terms of a data set. So I give you a data set, and this is a typical data set that is used by research or experiment that's done by researchers where maybe they have a small plot of land and they apply some pesticide to it. And in this land, they happen to know maybe there are 10 scorpions. And after they wait for a while, they count, well, how many scorpions died? So they might try a dosage level of, let's say, I don't know, I'll just make this up, 5 milligrams. And then they'll try another dosage level of 10 milligrams on a new plot that maybe has 10 scorpions as well. How many died? Using that, then, you have binomial observations, and you can fit a model that uses dose as the explanatory variable to try to estimate the probability of success in terms of killing. Once you have that model, then you can do the back the back prediction, where suppose now you say you want to make sure that your pesticide does kill 90%. Well, based upon my model that I've just constructed, what should be my dose, or X? So that's problem number 22. Are there any questions? Okay. So let's get back in the notes. We were on page 242. Okay. So our logistic regression model, represented like this, you can actually see, obviously, you're modeling the log of an odds of a success. The log odds of a success. And so intuitively, you might think, maybe odds ratios will help you interpret the effect that X has on the response. And so that's what we're going to talk about. So to make this simple, suppose we just have one explanatory variable. We'll call it just X. Here's what our model would look like. Now, since I have a natural log here, if I take my left-hand side, I take e raised to that left-hand side, e raised to the right-hand side, look what I get. My odds of success, which is a function of X now, is equal to e raised to the beta 0 plus beta 1 times X. So for example, let's say I want to know what's the odds of a success for a distance of, for a place kick with a distance of 30 yards. Well, it's simply e raised to the beta 0 plus beta 1 times 30. Now, oftentimes what we like to do is compare maybe a distance of 30 yards to a distance of 40 yards. Or how about, let's say, we can make the comparison for a C unit increase in distance. So C could be 10. So what we can do is also write out my odds of success on page 43 in terms of an odds of success where now I'm at X plus C. So where we saw X before, I replace it with X plus C. And now let's compare them. How do we compare two odds? Well, we take the ratio. So my odds ratio, or OR again for short, is the odds of success at X plus C over the odds of success at just X. And look what happens when I put in the exponential function expressions. Beta 0 cancels out with beta 0. My X here, which is a beta 1 times X essentially, crosses out with my beta 1 times X there. And look what I'm left with. Just C to the beta 1 up there. And what's so cool about this is that notice X is out of the equation. X plays no role at all. So in a practical sense, in terms of that place kicking example, what that means is if I want to compare a 30-yard field goal to a 40-yard field goal, my odds ratio will be exactly the same as one comparing, let's say, 45 yards to 55 yards. As long as I do that same constant increment. This is why logistic regression is the most used model for modeling binary responses. It's because when you interpret the effect that an explanatory variable has on the model, you can use these odds ratios, and the actual, let's say, value of X falls out. And it's only dependent upon how much you are increasing X by. Really cool. As you can see, I was kind of excited when I was writing this, and I put 3 exclamation marks there. Now, you can show this same expression, just like this, for the more general model that involves p explanatory variables. So if I were just to focus on xr itself, you can do exactly the same derivation that I just did here. Everything else falls out, and you're just left with c times beta sub r. Make sure you can do that. I've actually asked that on a test. This is actually a simple question on a test. Now, how do you interpret this odds ratio? Well, we need to interpret just a little bit differently from section 1.2 because we are not just comparing one level. I'm sorry, we're not comparing two levels of a binary explanatory variable. So we have to make a small adjustment. So here is a standard interpretation that you can use pretty much for any problem. The odds of a success change by e raised to the c times beta 1 times for every c unit increase in x. That's it. Again, you're comparing essentially two levels of x, like 30 to 40 yards. So you're comparing for a 10-yard increase. But again, it doesn't matter what you're starting off with for x, because it falls out from the mathematical expression. Well, let's say that we did have an x explanatory variable that was binary. Just to show you what happens. So let's say that x has two levels, 0 and 1. Remember number 1 on project number 2? That the type of potato chip. Remember how we inserted that value, that variable that was either 0 or 1? So pay attention. So notice if I look at the odds when x is equal to 0, look what happens. 0 times beta 1 is, of course, 0. So I have just e to the beta 0. When x is equal to 1, then I have a beta 0 plus beta 1 there. Let's take the ratio of the two to calculate the odds ratio. Beta 0s fall out. I'm left with just e to the beta 1. This is equivalent to saying c equal 1, which makes sense. If x is equal to 0 or if x is equal to 1, you can only have a c equal 1 unit increase. So in this situation, then you can go back to section 1.2 and use that same kind of interpretation that we saw then. The odds of success are e to the beta 1 times as large for x equal 1 than for x equals 0. Now, of course, like on a project or a test or outside of this class, hopefully you replace what x equal 1 is and x equals 0 is in the context of the problem itself. So, 1 could be the regular potato chips, 0 could be the Lystra potato chips. How do I find estimates then? Well, the maximum likelihood estimate of this odds ratio, guess what? You just put the hats on top of the unknown things, and you get OR hat. That's my maximum likelihood estimate. What about confidence intervals? So this goes to page 245. So a walled confidence interval can be found, first of all, for beta 1. So how do you find a walled confidence interval for beta 1? Beta 1 plus or minus 1 minus alpha divided by 2 quantile from a standard normal times the estimated variance of beta 1. Okay? But remember, we actually have e raised to the c times beta 1. So how about, that should be a half. How about instead we put a c in there? And then put an e there. So we take e raised to the confidence interval power, and that's my confidence interval. One interesting note, and then we'll end with this. Notice how I have a c here. Well, there's a nice little property, and we kind of saw this before, and that is, suppose I have a random variable, we'll call it w, and I have a constant a. The variance of a times w, I guess I kind of have it down there already, is a squared times the variance of w. Many of you have probably seen this in the class before. So if I apply that same technique there, this c here, I can pull that out, put it over here as c squared. But notice how I have a square root. It's underneath the square root still. So I can pull this out further as just c. And so that's where I get this expression. And as you might expect, wall confidence intervals don't work as well as we would like. So what we're going to do is use some kind of likelihood ratio type of interval, which we will talk about next time. Are there any questions? Okay, that's it for today.